Hi everyone, you are welcome back to my class. Today's topic is centered on work, heat and energy. We are starting with work. Work is one of the elementary energy transfer. In mechanics, work is said to be done whenever a force moves a body through a certain distance. Here in thermodynamics, we are going to look at work that is done in a piston cylinder arrangement. Let's consider figure 1. Figure 1 shows a piston cylinder arrangement. When the gas is heated, the piston moves outward. Now let's look at the mathematical proof of the formula for work done in a piston cylinder arrangement. Now work is the product of force and distance L. We go back to our fundamentals where we have pressure to be defined as force over area. Force over area. Now let's substitute the pressure force in equation 1. We have work equals the pressure multiplied by the area and the distance. If the piston moves an infinitesimal change in distance dl, then the infinitesimal work done is given as change in W equals to P multiplied by change in volume. Now we integrate change in volume with respect to state 1 to state 2. So therefore we have the work done from state 1 to state 2 equals to P integral change in V. Therefore, the expression becomes P into bracket V2 minus V1. That is the work done in a piston cylinder arrangement. Now we are going to look at work done in various quasi-static process. So we're starting with a constant. The first one is constant volume. Our second one is a constant pressure. The third one, constant temperature. The fourth one, the polytropic process. And the fifth one is adiabatic process. So we are going to look at the work done in these 5 processes that I have just written on the board. Now we are starting with constant volume process, which is also known as isochoric or isometric process. Isometric process. This process occurs when the volume is held constant during the process. This can be illustrated using a PV diagram as shown in figure 2. PV diagram. Going back to figure 1, when the gas is heated, the piston moves outward, thereby increasing the pressure from state 1 to state 2. Also, when the piston cools, it comes back from state 2 to state 1. So this PV diagram shows the isochoric process. Here, V1 equals to V2, but the pressure changes from state 1 to state 2. The line, this particular line is called the Isochoric line, which is parallel to the pressure axis. Now, what is the work done during this process? The work done during a constant volume process is taken as 0. Going back to equation 1, we have P into bracket V2 minus V1. Since V1 equals to V2, which is, let's give it a value. For example, if it is 5 meter cube, therefore, the work done will be P into bracket 5 minus 5, which becomes 0 multiplied by 5 is 0. This shows that the work done in an isometric process is taken as 0. The next one is isobaric process. Isobaric process. Isobaric process is a process in which the pressure is held constant throughout the process. Going back to the PV diagram, we can illustrate this in figure 3. The P and the V diagram. This is state 1 and this is state 2. At this level, P1 equals to P2, while the volume changes from V1 to V2. The line, which is in horizontal form, is called isobar. Now let's go back to the work done during this process. The work done in isobaric process is given as P into bracket V2 minus V1. Here, P is constant. The third one is isothermal process. An isothermal process, this is a process that occurs when the temperature is held constant throughout the process. This can be illustrated on the PV diagram as shown in the figure below. PV diagram. If this is 1 and here is 2, here is P2 and here is P1. Here is V1 and here is V2. The line is called isotherms. And the expression is given that PV equals to C. That C in that case is referred to as the temperature that is held constant. Now, the work done during this process will be determined. The work done is expressed as integral P dV. For an isothermal process, PV equals to C, which is the same thing as PV equals to P1 V1. So making P the subject of the formula, we have P equals to P1 V1 over V. Substituting this equation in equation 1. Substituting equation 2 in equation 1. The work done becomes P1 V1 integral 1 over V dV, changing from state 1 to state 2. When you integrate this expression, you have P1 V1 ln V from state 1 to state 2. Therefore, the expression for that becomes P1 V1 ln V2 over V1. Following this expression, PV equals to C. Therefore, we want to also relate the work done, which is in terms of V2 over V1, in terms of P1 over P2. Definitely, the work done can also be expressed as P1 V1 ln P1 over P2. This is the work done in an isothermal process. Polytropic process. This is a general thermodynamic process that involves some special processes. Any form of expression that comes in the form of PV raised to the power of n equals to C. Such expression is known as a polytropic process, where n is defined as the polytropic index. Now, how do we determine the work done in this process? Following in this case, we are going to make from equation 1, we make P the subject of the formula. When we make P the subject of the formula in equation 1, it becomes P equals to C over V raised to the power of n. Then substituting equation 2a in equation 2. The work done becomes P becomes C integral 1 over V raised to the power of n dV. Integrating this expression, we have C into bracket V raised to the power of minus n plus 1 divided by minus n plus 1. This is ranging from state 1 to state 2, which is also the same thing as C into bracket V raised to the power of V2 raised to the power of minus n plus 1 minus V1 raised to the power of minus n plus 1, all divided by minus n plus 1. Recall that C is defined as PV raised to the power of n, which is also P1 V1 raised to the power of n, which is the same thing as P2 V2 raised to the power of n. At this level, you use C to expand the bracket. At state 2, C becomes C multiplied by V2. At state 1, C will take the shape of P1 V1. So going back to this expression, W becomes C at state 2 becomes P2 V2, P2 V2 raised to the power of n multiplied by V2 minus n plus 1 minus C multiplied by state 1. We are taking state 1 of this P1 V1 raised to the power of n multiplied by V1 raised to the power of minus n plus 1 divided by minus n plus 1. By the time you simplify the equation further, we have P2 V2 minus P1 V1 over minus n plus 1. Let me just take an example. Taking V2 raised to the power of n, V2 raised to the power of n multiplied by V2 raised to the power of minus n plus 1. That minus n, according to indices, it becomes 1 over V2 raised to the power of n multiplied by V2. This cancels this. That is why we are left with the expression of P2 multiplied by V2 in this case. So we can simplify this equation further by multiplying the numerator and the denominator by a negative sign, so that the expression becomes P1 V1 minus P2 V2 over n minus 1. This is the work done in a polytropic process. Also, if you refer back to an ideal gas equation, which takes this form, PV equals to RT. Therefore, P1 V1 equals to RT1 and P2 V2 equals to RT2. Now, the work done can also be expressed as RT1 minus RT2 divided by n minus 1. Something is common here. R is common, which is T1 minus T2 over n minus 1. R is known as the gas constant, which is measured in joule per kilogram Kelvin. The PV diagram for an isothermal process, isochoric process, and isobaric process can be represented in a single PV diagram, which is as shown here. Here n is infinity. Here n equals to 0, and here n equals to 1. At this level, at n equals to infinity, we have a constant volume process. At n equals to 0, we have an isobaric process. And when n equals to 1, we have an isothermal process. A typical example is PVn equals to C. When n is 0, we have V raised to the power of 0 is 1. P equals to C. We have isobaric process. When n is infinity, we have isochoric process. And when n is 1, we have an isothermal process.